Okay, in this video I'm going to do these two problems. They are from Bender and Williamson number theory, and this is problem 1.15 from Bender and Williamson number theory. It says to factor each of these into a product of distinct primes. And what I'm going to do, I kind of worked out these beforehand. I used a calculator. But basically what I do to approach these is make sort of this tree diagram. Or as long as it's even, I divide by 2. So it's even, and I divide by 2, and I get 702. Still even, so I divide by 2, and I get 351 here. Now, I can tell it's divisible by 3 because 3 plus 5 plus 1 is 9, which is divisible by 3. If you add the numerals in the number, and it's divisible by 3, then the number itself is divisible by 3. So I know this is divisible by 3. And I get 117 here. And you might think 117 is prime, but it's not. It's divisible by 3 because 7 plus 1 plus 1 is 9, which itself is divisible by 3. So I go 3 times 39. And finally, I recognize 39 is 3 times 13. And so 1404 is 2 squared times 3 cubed times 13 to the 1 power. And that's the prime factorization of that number. 9702 starts off the same way with a 2. And let's see, 9,000, half of that is 4,500. Half of 700 is 350. 4,500 plus 350 is 4,850. And then it's 4,851 when I include the 2. That's not even. But let's see if I can divide that by 3. 4 plus 8 plus 5 plus 1 is 12. Is 18? Yes, it is divisible by 3. And I get a 16, 1617 here. This is again divisible by 3. 1617 gives me 539. You can either do these divisions yourself or use a calculator. 539 is 7 times 77, it turns out. And 77 is 7 times 11, which is its prime factorization. So 9702 is equal to 2 to the 1 power. I'm just counting the number of primes. I got 1, 2, I got 2 3s, 2 7s, and an 11. So I can write 2 to the 1 times 3 squared times 7 squared times 11. Finally, 89,250 is even, so I get twice 44,625. Now this is divisible by 5 clearly, so I guess I'll just divide by 5 here. 8925. Again, clearly divisible by 5, so I'll go ahead and factor that out, and I get 5 times 1785. Still clearly divisible by 5, and I get 5 times 357. Now this is not even, and it's not clearly divisible by 5, but 3 plus 5 plus 7 is 15, which is divisible by 3, so this whole thing is divisible by 3, and I get 119 here. And 119, it turns out, is 7 times 17. And therefore, 89,250 is, let's take these guys in order. Let's take the 2, then the 3, then the 3 5s, then 7 and 17. So it's 2 to the 1 times 3 to the 1. You don't have to write to the 1 power. Times 5 cubed times 7 times 17. Okay, and that's the answer to problem number 2. I think I got time to do problem number 3 in this video, so I'm going to go ahead and do it. So those are just a couple of examples of some prime factorizations. The next problem is problem 16 from the number theory chapter of Bender and Williamson. And it says, let n equal p1 to the e1 ... pk to the ek. Okay, that's a p sub k raised to the power e sub k. And basically what they're doing is saying that this is the factorization of n into powers of distinct primes, where m is greater than or equal to 1 is some integer. And we're going to raise that number n to the mth power. Okay? And what we're going to do is we're going to write the prime factorization of n to the m, and we're going to use the fact that x to the a raised to the b power is equal to x to the a times b. Okay, so for example, x cubed squared is x cubed, x times x times x squared. So it's x cubed times itself. So I multiply one more time, times x times x times x, and this is x to the sixth, obviously. Okay, it also uses the fact that x to the a times x to the b all raised to this. Well, let me write it more simply. It also uses the fact that x times y raised to the a power is x to the a times y to the a. And these are simple facts about exponents. And what we're going to do then is we're going to write n out as p1 to the e1 power, p2 to the e2 power, p3. I'm going to write out a few more terms than he did here. He just did p1 and pk and put dot, dot, dot in between them. But I'm going to write out 1, 2, and 3. And pk e to the k. So for example, if we look at our 89,250, p1 would be 2, e1 would be 1, p2 would be 3, e2 would be 1, p3 would be 5, and e3 would be 3. P4 would be 17 with an e4 of 1, and p5, k would be 5. P5 would be 17 with ek, or e5 to be to the 1th power, because these are both 1s here on the 7 and the 17. Okay, so it's just an example of a general form of a prime factorization. Now we're going to raise n to the m power. And so I take this whole thing, p3, e3, dot, 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 pk to the ek. I take this whole thing and raise it to the m power. And the first rule I'm going to apply is this one here that says when I have the product of two numbers raised to some power, it's just each of those numbers raised to that power multiplied together. And so I'm going to say that this is p1 to the e1 all raised to the m power times p2 to the e2 all raised to the m power times p3 to the e3 all raised to the m power times dot, 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 pk to the ek all raised to the m power. And finally, I'm going to apply now the other rule of exponents. X to the a all raised to the b is x to the a times b. And I'm going to write this is p1 m to the m times e1 power, p2 to the m times e2 power, p3 to the m times e3 power, dot, 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 pk m ek power. And what this does is it just multiplies all the exponents in the prime factorization by m. So if I take a number and cube it, so for example, if I take 1404 and I cube it, then I'm just going to multiply each of those exponents by 3. 2 to the 2 times 3 times 3 to the 3 times 3 times 13 to the 1 times 3, which is 2 to the 6th times 3 to the 9th times 13 cubed. Okay? So there's an example of that where m, the power that I'm raising it to, is equal to 3. Okay? So I hope this helps. There's the final answer for that one. I hope this helps and that you see how we applied these rules of exponents to this problem.